This is a lesson over the law of universal gravitation. For this example, we'll be looking at a satellite that is orbiting the Earth. This satellite is orbiting the Earth at 3 times 10 to the 4th meters away from the surface of the Earth, which I've labeled as the radius sub s for a satellite. We also know some other information such as the radius of the Earth, which is 6.38 times 10 to the 6 meters. And we also know the mass of the Earth, which is 5.97 times 10 to the 24th kilograms. And of course we have our universal gravitational constant, which is shown as the uppercase G, which is equal to 6.67 times 10 to the negative 11th newtons meter squared per kilogram squared. And so for this example, we're going to want to find the speed and period of the satellite that is orbiting the Earth. So let's go ahead and start with solving for the orbital speed. And we have an equation for this, which is our orbital speed would be equal to the square root of our universal gravitational constant multiplied by the mass, which is the mass of the Earth, divided by the radius from the center of the Earth. So now this radius, we can't actually use the radius of the Earth or the radius of the satellite. We actually want to find the total radius. So let's do that real quick. And that's just simply adding the radius of the from the surface to the satellite, and also adding it to the radius of the Earth. So if we go ahead and do that, let's see here, we should come up with a total radius of 6.41 times 10 to the 6th meters. Okay, so now that we have that, now we can actually substitute in to find for our velocity here. And so let's go ahead and do that. So this will take some number crunching, as well as a bit of unit conversion. Nothing too bad though. So I put in the universal gravitational constant. Now we want to put the mass of the Earth, and all of that will be divided by our radius that we just found, which is 6.41 times 10 to the 6th meters. Okay, and so when you look at these, the units don't really cancel out all that well. So really what we have to do is we have to use take newtons back to what it actually is derived from its base units. So if we do a simple unit conversion, we know that 1 kilogram meter per second squared is the same as 1 newton. So now let's go ahead and try to cancel some units to make sure that we get units of a velocity, of a speed. So we can first cancel out newtons, and then if we look through here, we can see that in the top we have kilograms on the top twice, and then it's on the bottom squared here, so those will reduce to 1. As well, we do have a, let's see here, we have meters squared in the top of our gravitational constant, and we have meters in the top of our conversion factor that we use, and then we have meters in the bottom. So I'm just going to cancel out the meters from our conversion factor and on the bottom to reduce to 1. And so now we have, really what's left is our meters squared and our over second squared. So really, whatever value you get here, it should be meters squared over second squared, but we remember that we have to take the square root. So what our speed should come out to be once you do all that number crunching is 7.88 times 10 to the third meters per second. So that's how you solve for the orbital speed. So let's go ahead and try to solve for the period. Now the period is just the total amount of time that it would take the satellite to go around the Earth. And so our equation for that is the period is equal to 2 pi multiplied by r cubed, so the radius cubed, over the universal gravitational constant multiplied by the mass of the Earth. So now we have all these numbers, so we're just going to have to plug and chug from here. So we have t is equal to 2 pi multiplied by, and now inside of our square root we have the radius cubed, so 6.41 times 10 to the 6th meters, that's cubed. And we're going to have all of this over, we know we have our universal gravitational constant, and that's multiplied by the mass of the Earth, and we know we have all of this under a square root. What we also must remember though is we're going to have to do a bit of unit conversion here too, just to make sure that our units cancel out. So again, the problem will be is that we have newtons in here and we have to make it go to its base units. So we'll have 1 newton here over 1 kilogram meter per second squared. So let's go ahead and try to reduce our units here. So we know we have newtons on top and newtons on bottom. We know we have meters cubed on top, so we should be able to find that on the bottom. So if we get rid of that, we'll have 2 of them there, and then there's another meter here. So that takes care, because the top is meters, it will end up being meters cubed. Once we cube the radius, we have to find meters cubed in the denominator as well. And in our denominator, we do have kilograms twice, so that's kilograms squared. But in our denominator, we also have over a kilogram squared, so that's really is more like it's in the numerator. So we can reduce those. So the only units that we're left with is seconds squared, which is in the denominator of the denominator, if that makes sense. So really, it should be in the numerator once we figure all that out. So once you go ahead and plug and chug from this point, you should get that your period is equal to about 5,110 seconds, or 85.2 minutes, which is also equal to 1.4 hours. So as you can see, the law of universal gravitation, it helps us be able to calculate different things, which includes orbital speed and orbital period.